right, everybody, welcome to Full Momentum and HEC-RAS podcast. I'm your host, Ben Cary, and joining me as always today is Chris Goodell. We also have our special guest for this episode as well as the previous episode, Gary Brunner. Welcome, Gary. For those of you guys who are tuning into this video and weren't able to see the previous episode, Gary and us spent time discussing the new HEC-RAS 6.0 version release. We got into the history of HEC-RAS as well as some of the new features, including spatial precip and infiltration and 2D bridges in the previous video. So if you're interested in those topics, you haven't had a chance, definitely recommend you guys going back one video, checking that out. This is going to be a continuation of that previous discussion. We're going to get into some more topics with the 6.0 release today, as well as kind of what's next for HEC-RAS. So with that, Gary, I'm going to throw it back to you to continue your conversation. I believe you may be talking about the new WindForce part of HEC-RAS 6.0.
Before you go, Gary, let me just say real quick, if you guys have not watched the previous video, pause this one right now and go watch it, because we talked about 2D bridges, we talked about spatial rainfall and infiltration, and these things are so cool. And so you've got to watch that.
Don't want to miss it.
And now we get to talk about wind. So Gary, let's hear about it, man.
Well, first of all, Chris and Ben, thanks for having me again. Long time no talk, right?
Yeah. What has it been? A whole 10 minutes?
Yeah. All right.
Actually, we all got the same clothes and put them right back.
Right. The magic of editing, though. It's going to be, as I understand, it's all Ben's magic of editing, right, Ben? You're the editor?
It's a team effort.
Oh, okay. Chris does some of that too. All right. Well, I'm going to go ahead and share my screen then, and we're going to jump into WindForces in RAS 6.0. So we've added WindForces to RAS, but we did it for both 1D and 2D. And first of all, I need to thank for the Tennessee Valley Authority, actually, because they actually funded this.
Cool.
If you're interested in wind and you're interested in wind in RAS 6.0, you got to say thanks to TVA, because it wouldn't have happened without their funding. So originally they wanted to fund us just to do 1D wind, and I said, oh, no, we can't just do that. We got to do 2D wind, because there's going to be more applications for 2D wind than there is 1D, and they agreed really quickly, so it was great, and they were right on board with it. So we actually have wind capability for both 1D finite difference, but we also have this new 1D method, which we'll talk about a little bit, called 1D finite volume, and you can have wind forces in that. And then we have wind forces in 2D. Now, if you're doing 2D, you can't do diffusion wave and have wind forces, because diffusion wave is already a subset of the full set of equations. So what would be the point of adding in wind if you don't have the acceleration terms? It would make no sense. So if you're going to do wind, you have to use the full shallow water equations. We do have two shallow water equation solvers now. Previous versions, there was only one, but there's a new shallow water equation solver also that you might want to check out that's semi-explicit method and very conservative on the solving the momentum, and it also can do wind capabilities. So
what is that one called?
We have some names in there. It's just SWE. There's one called ELM for Eulerian Lagrangian, and then there's one just a method, and then the other one's just SWE shallow water equations EM for Eulerian method, and the new one is only Eulerian. I don't want to go into explaining all that because it's a long discussion, but we could have that as another discussion at some point. But that's talked about in the 2D users manual. So if you want to learn about that, go to the 2D users manual.
Okay.
So wind is spatial data, just like precipitation can be. And so as far as data sources, you can get that as grids. In our case, in the US, we get that from the National Weather Service. But there's also point data. So you can enter point data into RAS, and then it will interpolate winds from the point data. Obviously, the gridded data is going to be more spatially accurate. That's the best way to go. But if you only have point data, you can still do wind forces in RAS. It's just we did lots of different verification of wind data sets in RAS. This is just one of the 2D ones, and it's kind of interesting one because you have a circular 2D model, okay, and you have all the cells in here. And then for the top half of the circle, you apply a wind force from left to right with a constant wind. In the bottom half, you apply a wind force from right to left. And there's actually an analytical solution to this. And in fact, this top model is the analytical solution. Okay. And so the red color are higher water surfaces. The green is 0 elevation. and then the blue is a negative elevation. So if you think of a water surface in a tank at water surface at elevation 0, the tank's deep, and then you apply the wind forces, you get a rise in the direction of the wind. It goes to red. And since this wind is going this way, you get a rise here and you get a lowering here. So this is actually an analytical solution to this problem. And then we did the same model in RAS, exact same mesh, okay, exact same wind field, and sure enough, we get the same answers. So this proved to us that we were solving wind forces accurately in a 2D domain, okay. And we had other simpler data sets, more kind of 1D data sets, and other 2D data sets that we verified analytical versus computational solutions for these wind fields.
Correct me if I'm wrong, Gary, but wouldn't this just set up a whirlpool pattern if you ran it long enough?
No, because the wind is just constant to the left this way and constant to the right. Okay, so it's going to hold. If the wind was such that you didn't have the same wind field, we have the same wind going to the right and the left. Okay, but it's just splitting it in half. So we did actually run RAS with that wind field as a constant over a long enough time, then it settled down to this answer.
But you're still getting I imagine you're getting, if you were to turn on velocity tracing.
Oh, okay. Oh, yeah. The velocity's moving, but the water surface is constant. I'm sorry.
So it's kind of going around like this. It'd be going around the perimeter. It's like a wave, basically. You'll have a standing wave there. Interesting.
So I want to show some animations from a recent event. So we applied, I shouldn't say we, but actually our New Orleans district office applied the RAS 6.0, kind of a pre-beta version that we gave them to test this out on, to a couple of hurricanes. And so this is just going to show some results from Hurricane Laura. So this first animation is just going to be, this is right in RAS Mapper. Everything you're seeing is straight from RAS and RAS Mapper. This isn't any third-party software showing the visualization. So the first thing is going to be the precipitation that we modeled and had brought into RAS. So here's a little animation of the precip. And so this plot is just darker colors is more intense precipitation. And here comes the hurricane. You can see the eye of the hurricane, but this isn't wind. This is just showing the precip that's falling. Okay. So that's an input source into this model in RAS. Okay. Then the second input source, though, is the wind data. And so here's going to be an animation of the wind field. And this hurricane was a Cat 4 when it hit. And so you're going to see velocities are going to be upwards of 190 feet per second. So this is showing it in feet per second. Often we see reported on the news wind fields in miles per hour. Probably this would have been like 130 to 140 miles per hour wind fields when it was a Cat 4. But in feet per second, it's like 190 feet per second. Okay, so here we go. And here's going to be an animation of the wind field. This is right, the wind's brought in to RAS Mapper and the wind field that's applied to the 2D model. And here comes the hurricane wind field. I'm going to stop here. I'm going to turn on, show you that there's 192 feet per second, but in the eye of it, it's like 1 to the minus 12, virtually 0 feet per second. Okay, I'm going to turn on the velocity tracers. So you can turn on the velocity tracers for the wind field also.
Oh, that's cool.
Yeah. So that's cool stuff. And then we'll go ahead and finish the animation. Right now, it doesn't do combined velocity tracers with the animation, so we're going to work on that, and it will. Okay, so now let's look at the water surface. Now we're going to plot the water surface. So I want to point out the legend. This is 0 elevation, this green, and then it goes up to 20. This particular model had showed some water surface elevations right at the coast of over 15 feet. So we're going to be up in this kind of pink area. So let's go ahead and animate that. And so here we go. The hurricane's pushing in. It's pushing the water surface up against the coast. There we're hitting the peak, and it's moving in and passing through. Now I'm just going to press the max button to get a max water surface. So there's the max water surface that occurred everywhere during it. And I can see from the mouse, and it got to 15.3 right at the coast, kind of at where the highest winds were pushing the water into the coast. Okay.
And this is just starting with basically stagnant water, right? And all you're doing is putting wind on it.
It was stagnant water, but there was water inland coming down some of the streams. So this is actually a real model. But for the ocean, it was just an ocean boundary condition. Now we did out in the ocean have a boundary condition from AdCirc, okay, of a water surface. But that water surface was far out in the ocean that it only kind of came up to about a foot above 0. Okay. So this complete rise of this water surface inside this domain is completed from RAS. Now, I do want to point out, RAS is only modeling the winds. Currently, we're not modeling the pressure forces of the air, okay? And we're not modeling wave forces, which ADCIRC does model. So ADCIRC's a more complete model of what's happening on this coast. But it's pretty cool that you'll be able to kind of do dual modeling where you combine ADCIRC and RAS to coastal projects, and you have the wind forces in both models. Okay.
Yeah.
And where that line is depends upon what you want to do for the modeling. So in this case, I'm showing RAS out in the ocean, but probably more often than not, you'd have ADCIRC for the ocean, and then marry the two up at the coast, okay, or even inside the coast, and let ADCIRC give you the results to the coast. But just showing, but RAS is accounting for the wind forces, and you can do stuff like this right in RAS, at least on a limited basis, accounting for the wind force terms part of this.
Very cool.
I imagine you, for a really cool picture, you could put the particle tracing for wind on top of this.
Yes.
And you could see exactly how that wind is setting up the higher water surface. Yeah.
Cool stuff.
I think you might start getting calls from like your local weatherman. Maybe not in Davis, but maybe down in
yeah, not a lot of need for this
area.
Well, the New Orleans district was super interested in this because they do have all kinds of applications, as well as our Fort Worth district and, our Florida districts, et cetera, et cetera. There's lots of any coastal district or coastal engineers, there's going to be applications for doing this kind of work for hurricane type of events. Yeah. So this is a big deal if you live and work on the coast.
Well, potentially like wave run-up work on reservoirs as well.
There's another application, absolutely.
They use it for that too.
And that's kind of what TVA wanted it for, which they have a lot of large reservoirs they're responsible for and that they generate power with, but they can get some major wind forces on those reservoirs and get some major wave run up, and they wanted to be able to model that more accurately.
Now, how difficult is it to find accurate wind data to the level that you needed to model something like this?
Well, it's not easy. It's not everywhere, obviously. Obviously, the Weather Service is outputting both historical winds, which is what this was from, and they also do wind forecasting. So if you're in the middle of an event, you're going to get wind forecasts from people like the Weather Service, or some of these atmospheric models might be predicting, what's going to happen over time from an atmospheric standpoint. So you might just take the wind field computed from an atmospheric model would be another approach. Yep. But as far as historic data, you want observed winds. Most likely in our country, in the U.S., you're going to get that from the National Weather Service.
So is, you said you can get gridded wind data. Is that gridded wind data compiled or collected similar to how gridded rainfall data is from
I'm not going to
radar source, or?
I do not know all the ins and outs of how they do and come up with the wind fields in the Weather Service for grid. So I'm not even going to try to answer that equation because I'd probably be wrong. So, so I'm really not sure on that. I'm just more of a user of that data than someone involved in how it's developed. So
sure.
Yeah.
Nice. I love it. That's great.
So moving on to the next topic, one of the other capabilities we added is a new 1D solver. And a lot of people are thinking, well, why are you even working on 1D? Okay, well, 1D is still going to be used for a lot of problems. There's a lot of really large river systems that are very confined, and 1D modeling is plenty accurate for a lot of these systems. Like I have this huge model of the Allegheny, Monongahela, Ohio River system. And back in that area, the rivers are very confined. There's very little floodplain, okay? And water comes down the rivers. There's not much floodplain at all. And the water surface acts very much one-dimensional. It's going down the stream, okay? And 1D models are plenty accurate for the water surface and so much faster, okay? 100 times faster. Yeah. That whole model, I can run a 2-week simulation in 5 minutes. And it's over 1,000 miles of river system with bridges and dams and all kinds of stuff in it.
I know this particular feature is one of the ones that Chris is most excited about. So
yeah.
Oh yeah, I've been looking forward to this for a long time because I just think back to the amount of time I've spent troubleshooting models for this very reason, and trying to use the tricks and tools to keep keep it wet or to keep it stable when it's really low flow. And the fact that you can't directly model, say, a flash flood, where it is starting out dry and you literally have this wave of water that just moves through. And and Gary knows all about the Missoula flood model I built years ago in 1D, and that was very tricky to get started. Much easier in 2D for this very reason. But now I might have to do a 1D finite volume.
All you have to do is
take
your previous 1D Missoula flood model and flip a switch. That's it.
Yeah,
super cool.
To me, that's one of the coolest things about the 6.0 release overall is obviously there's like new features, which are just new and they're just cool. And there's additional capabilities with that. But it seems like one of the biggest takeaways from the release is that all the new components are going to allow you to use 1D or 2D in the most appropriate setting. So for instance, if you want to do, if the location that you're modeling is most appropriate modeled as 2D, but it has a bridge, now you can still do that as a 2D model versus previously it was like, well, we have to make some assumptions about this, or we can model it as a culvert, or we can do 1D, 2D modeling. But in reality, it should be modeled as 2D. Well, now you can do that. In the same way, there's going to be a lot of situations where, it's totally acceptable and better in a lot of cases from a speed standpoint to model this situation as 1D. Well, but we're going to have to do some workarounds, and we can't quite do that because we're doing some low flow modeling, and it might start off as dry. Well, now you can do that. And so there are a lot of these improvements seem to just make it easier to model the scenario that you want more appropriately, which is really, really cool. So.
Yeah. And so this is just another tool in the toolbox. Okay. And if you don't want to use it, you don't have to. That's the great thing about it. But there are going to be applications that people might want to do 1D modeling, and they might be in areas where the channel starts out dry, or maybe it's steep and they have to model low flow. The original 1D solver in RAS, the 1D finite difference solver, has some limitations. You can't let any cross section go dry. And in steep areas, modeling low flow is very difficult because the rapid changes in water surface from cross section to cross section with the finite difference approach causes instabilities. It just does. So it's actually more difficult to model low flow than it is high flow with that solver. This 1D finite volume approach, basically we stole this right from what we did in 2D. The 2D is complete finite volume. We thought, we can apply this to 1D because between cross sections can be the cells, okay? And the cross sections are the faces. And so now we've developed a method that you can start with dry channels. You can model low flow, no problem. You can model steep channels, no problem. Complete wetting and drying. It's very stable, can handle extremely rapidly rising hydrographs, automatically does subcritical and supercritical flow. You don't have to turn on a switch like you do for the finite difference one. It just does it, okay? It handles hydraulic jumps. No mixed flow option required. Nope, automatically handles supercritical flow and hydraulic jumps right out of the box.
Wow.
Okay, so, and I've done a bunch of experimenting with the hydraulic jumps with this. It works great, okay? And the supercritical and subcritical flow. So nothing. And the other cool thing is at junctions, we actually do a mini 2D solution, which I'll show here in a second. So for the cross sections, it actually breaks up the cross section into 3 compartments, a leftover bank, a main channel, a right over bank. And so there's really 3 kind of finite volume cells in a cross section. However, they have this limitation that they have the same water surface at each cross section. So flow is still going to be transferred based on conveyance and the assumption of a single water surface per time step. But it's really 3 finite volume compartments because the left of the leftover bank and the channel and the right over bank can have different lengths, so there's different volumes in those compartments. So think of it as 3 cells with this requirement of the same water surface at the ends, okay? At junctions, though, what we're doing is you have to lay out the finite volume model spatially. You can't do a stick figure. It has to be a real spatial layout, because it's going to take your layout and then from the cross sections around the junction, it's going to form a 2D cell. It basically connects the ends of the cross sections, and that is a 2D cell. So while this is 1D, at the junctions, it does a 2D calculation. So it takes into account the angle of this water coming in, the volume within the cell. It also takes into account the momentum coming in, the velocity, and how that affects the result of the water surface on the cell and how it leaves. So that's really cool. So even though you're doing 1D modeling, the junctions are a simple 2D cell. Okay. So no more huge concern about, where do I put the cross sections exactly, and if this thing, the tributary is much higher than the main stem. If I only have water in the main stem, no worries about that anymore.
And as flow goes up and down, you can see the hydraulics change in that junction area, whereas it doesn't with the traditional method.
Right.
Nice.
So let's just look at a couple examples. Here is our friend Bald Eagle Creek again, and we're going to apply this inflow hydrograph. We're going to start this completely dry. And so I'm just going to show that no trouble starting dry and wetting, going to a maximum water surface. And then we're going to run it all the way back to a zero flow. And so you'll see upstream on the right, it's going to start to dry out. Now, water can get trapped between cross sections though. So if you go low enough, like this water's never going to get out. Okay.
Yeah.
Okay.
It's just weird to see, like, as it was coming down, I was getting like,
anxious
bad feelings. Yeah. Just
waiting, too. I was
waiting to see the red
Gary,
show
stop
up.
It. It's going to crash.
Waiting for the energy grade to spike.
Right.
That's true.
Oops, okay. So
especially the beginning there, watching that wave come down, that's really cool.
Right.
Yeah.
So here's that same model, but I started with a base flow because now I'm going to run the blue one's the finite difference method and the red one's the finite volume method for the same event, but starting with a base flow and ending with a base flow. So it's not going to start dry, it's not going to go dry, but I'm going to compare the older finite difference with the newer finite volume. Same hydrograph. Okay, that doesn't tell you much. They went up and down together. Okay, yeah. But here's the hydrographs. They both started with the same inflow, which is the blue with the squares. But then at the very end, the pink one is the finite volume hydrograph and the green one is the finite difference hydrograph. So basically the same shape, same timing, same peak flow. A little bit difference on the rise. The finite volume actually got downstream a little faster and a little bit difference in the shape, okay, but the exact same volume. And pretty much as far as the peak, same timing and same peak magnitude. So they're not going to give exactly the same results. They're a different approach. It's a very different approach. So even with the same cross-section, same end values, you're not going to get exactly the same answers, okay? And so when you switch to finite volume, you might have to recalibrate slightly depending upon what you get for an answer, okay? Because it's a very, very different approach.
So intuitively, I want to say, correct me if I'm wrong, Gary, but I want to say with the finite volume approach, it's even more important that you have cross-sections spaced closer together so that you can approximate that volume. Okay.
It depends on the slope of the water surface, right? First of all. So if you're in a flat area, you can obviously still have cross sections really far apart. If you're in a steep area, yes, you want tighter cross sections. However, one drawback of the finite volume method is that it's a volume method. If cross sections are super close together, then that cell has very little volume, right? And the water surface in that cell will rise and fall based on much smaller changes in flow. And so if you have too small a spacing and basically have too small a cells, you're going to need to use very small time steps because you're going to have such a small cell and such small volume that for a given time step, when it brings in a flow and a volume, it's going to want to go up more before it computes the outflow, and it's going to have to iterate more to get that right. So in reality, there's some limit. Yes, you want to have smaller cells to capture the change in water surface, but if you make the cross sections too close together, the finite volume method, that's where we're actually going to have trouble with stability because the cell's too small, and you're going to have to, that will dictate using a much smaller time step to get it to solve accurately.
So you're getting into the Courant condition is more important for the finite volume.
Right, because it's kind of like a fill and release type of thing. How much water does it take to fill it over the time step and go out? Okay. Whereas the finite difference, because its solution is based just on change in water surface, cross sections real close together might not have very much change in water surface at all. So it has no trouble handling that. So that's one thing the finite difference method can do better than the finite volume is to have cross sections super close together. So one problem is people are going to have those models they developed with finite difference, and some locations are going to have cross sections like 2 feet apart. And then they're going to try to run it in 1D finite volume, and it's not going to work. It's going to go unstable at that location unless they use a really small time step. So you're going to have to get used to having, I don't need cross sections really close together. I really just need to think about cross sections based on change in water surface and having enough cells. Okay. So it's going to be a slightly different approach.
Is the computation of the volume in the 3 subsections, is that going to be based on the respective reach lengths, or is that being pulled out of terrain?
So currently it takes the terrain of the faces and then just the reach lengths to get the volume.
Okay.
And we did that on purpose so the results would be more similar to the current model.
Yeah.
Okay. But future versions are going to have an option that you can compute the volume based on the terrain.
Okay.
Like it does for 2D. Okay.
And
so right now the volume is really an average of the end areas, which is similar to the 1D approach right now. The volume between cross sections is an average of the areas. So if we didn't do it that way, the results would be vastly different. So I wanted to do that first on purpose. So if you started with your current 1D model that was calibrated, you could switch to 1D finite volume and it's not going to take a lot of change. You're going to get similar answers.
Yeah.
And you might not have to recalibrate at all. Okay.
Right.
But future, we're going to have an option that says, no, compute the volume based on the terrain. But that's not in 6.0 currently.
Okay.
Yeah. Good question.
Nice. Yeah, this is really cool.
Obviously, it handles bridges, it handles inline structures, it handles everything except for 2 things. It does not handle the Priceman slot pressurized pipe option we have in RAS. So if you have a model where you added lids on top of cross sections for pressurized pipes, you had that Priceman slot option, it doesn't do that. It's going to blow up right away. So it can't do it. Okay. So you can't do pressurized pipe flow with the 1D finite volume.
Okay.
Currently. Future version, we'll talk about that at the end of this.
Yeah.
The other thing you can't do is you can't combine currently modified poles routing with the 1D finite volume, but really you don't need to. We added modified poles routing to the current unsteady flow 1D stuff because the 1D finite difference couldn't handle low flow or dry flow or really steep reaches. And so you can use modified poles routing instead, but you don't need to do that with this 1D finite volume because it can handle all of that. So you can't run modified poles combined with 1D finite volume. So those are the only 2 things currently that we know about that you can't do when you turn on 1D finite volume. You can't do pressurized pipes, and you can't do modified poles intermixed with 1D finite volume routing in reaches. Won't work.
Okay, I see the Priceman slot being a very, very minor inconvenience, and really the modified poles, since you don't really need it with this technique. It's not an inconvenience at all. But
so yeah, if you had models that were using modified poles, just turn off the modified pole stuff and just use straight away the 1D finite volume everywhere.
Besides that, and let's say you're starting brand new, so you're not trying to match previous modeling efforts with a previous version, but if you're starting new, is there any reason not to go finite volume with 1D unsteady?
There may be. It turns out the 1D finite difference is generally a little bit faster computationally, and there's some reasons for that. The coding for the 1D finite difference was done back when computers were really small and really slow.
Yeah.
And when we coded that, everything was about keeping the memory footprint small, and every line of code, we didn't want any wasted code for computational speed.
Yeah.
The second thing, though, is that whether you realize or not, when 1D finite difference, you get the equations are developed for the main channel, and then the overbanks are actually combined into what's called a floodplain. So if you go into chapter 2 of the hydraulic reference manual and you look at the 1D finite difference solution, the equations show 2 compartments. So there's a channel compartment and a floodplain compartment. And that floodplain compartment is actually a combining of the left and right overbank into one thing. Okay. And so there's really only like 2 flow areas in the 1D finite difference for a cross section, channel and floodplain. Floodplains are combined. Okay. And because of that, it's averaging some properties for the left and right overbank, like the length and the friction losses. So the friction loss that's computed for the floodplain is an average of the left and right overbank for the 1D finite difference. Whereas the 1D finite volume, left bank is left overbank, channel's channel, and right overbank's right overbank, separate volumes, separate friction losses, the whole thing. So there's really 3 flood compartments in 1D finite volume. So it's doing more computations for the volume, more computations for the friction losses, et cetera. So that's kind of the major reason that 1D finite volume is a little bit slower than 1D finite volume. Now that's not going to be true of every data set, because there's going to be a lot of data sets that were running slow because the 1D finite difference had to iterate a lot, especially at low flow or rapidly rises. Okay, whereas the 1D finite volume might not have to iterate as much, so it might end up being faster. So it depends on the data set. Okay, but in general, if you had a very well-behaved model for both of them, the 1D finite difference is actually faster computationally than the 1D finite volume because of the reasons I talked about. That's the only drawback, as far as I'm concerned. Okay, here we have.
I'm super excited to try this out. Yeah, this is very cool. I kind of want to resurrect some of my old models and just run them in finite volume.
You definitely should resurrect that Missoula flood model, because now you can start it dry and see what happens.
I will do that. Yeah.
It'll probably make you sad, Chris, because you'll realize how much time you spend.
I mean, yeah, you're right. I spent so much time on that. But it's all good. It is all good.
So here's just an example with a bridge in it to show that 1D finite volume can handle bridge hydraulics, no problem. The answers aren't going to be exactly the same, because again, it's a volume-based approach versus a 1D finite difference, water surface difference approach. So it's very different, but let's just animate this. Here I'm showing the finite difference and the finite volume solution together. The finite volume solution is the one with the triangles. The finite difference in this case is the solid blue line. Okay, a little difference, they hit the deck. Okay, a little difference even downstream and upstream, just because differences from the finite volume approach versus the finite difference approach. Okay. But no problem going through, from low flow to pressure flow to weir flow. And here's a model where there's a ton of bridges, and I'm going to start the model dry, just so you can do wetting and drying even through bridges. So right through the bridge, no stability problems, right through the bridge.
Man, that's awesome.
Yeah. Inline structures work with 1D finite volume. Lateral structures work with 1D finite volume. All the connections for storage areas to 2D areas, the whole thing works with 1D finite volume.
So since it's using the same technique in 2D, correct me if I'm wrong, but at a given cross section, you're solving for water surface elevation and velocity, correct? Versus in the finite difference, you're solving for water surface elevation and flow. Do I have that right, or?
Well, even in 1D finite difference, velocity comes into play in the calculation of the momentum. Okay, part of it. Okay, at the face. So you're still calculating momentum at the face, but in 1D finite difference, it's calculating water surface and velocity / momentum only at the faces. Okay, whereas in the 1D finite volume, the actual water surface is calculated at the center of the cell, and then just the velocity and momentum only is calculated at the faces. So we actually have to interpolate a water surface at the faces.
Okay.
Okay, and then that interpolated water surface is used to calculate velocity and momentum. So it's iteratively solved. They're intertwined, obviously, right? Okay. Right. But that's the difference, though.
Okay. Nice.
Okay. Next thing was pump stations. We've had pump stations for a long time, but when 2D came out, we didn't have the ability to connect a pump station to a 2D cell. So now you can connect from a 2D cell to another 2D cell, or a 2D cell to a storage area, or a 2D cell to a 1D river reach, whatever you want to do.
What was the biggest reason that you weren't able to do that, Cary?
We just didn't have the time or the funds to do it. There was no computational reason at all.
Got it.
It was just, you can only do so many things.
Sure.
And this got kind of dropped off when we decided to release the first 2D. I wanted to get 2D out there with what we had, because even what we had with 5.0 was a lot you could do in 2D.
Yeah, totally.
And then look at all the things we added in 5.04. We added a bunch of new capabilities in 5.04. And then now we've added a bunch of more capabilities in 6.0 along those lines. So if we would have waited till we had everything, like bridges and other pumps, it would have been way too long before putting out a version that could do 2D. So
yeah.
So that's why we made the decision. So there's a whole laundry list of features that we have that we're planning on working and even started working on that aren't in 6.0. Okay, so we'll talk about some of those in a little bit here.
Yep.
So here I just have an example where this is a 2D area, this is a storage area, and this is a 1D river reach. I can spatially connect this cell to this 1D cross section, this cell to this 1D cross section with a separate pump, this cell to this storage area with a separate pump. I can also connect from a 2D area to out of the system, in other words, not connected to any element, and I can connect from a 2D cell to another 2D cell. In this example, it's hard to see, but there's two pump lines, one going from this cell to here and one going from this cell to there. I just did this for fun, where I put in two pumps, and basically I'm pumping uphill. This is a mountain over here, I'm pumping the water from the valley up to this hill, and then I'm letting it run back down the hill. And I just did that as an experiment for fun. Obviously, you probably wouldn't be doing that, but. And so here it's just showing the pump editor, okay? And what you have to do for each pump, when you click on the pump, you have to give it the X and Y coordinates. So you start where the from is, you give the X and Y coordinates, and it can be multiple points. So it doesn't have to just be 2 points, a straight line. You can actually depict it at however the pump line is, okay? So you give it the coordinates. And then you have an on and off water surface elevation that you define for each pump, and you have a head versus flow pump efficiency curve, okay? And you can even control how long does it take to ramp up to full flow capacity, how long does it take to shut down, what's the width of the pump, et cetera, et cetera. Okay.
So Gary, I had to ask, one of the things, this isn't actually pump related, but I can see how it connects now. One of the things Chris and I have run into in the past is oftentimes if you have, for instance, an SA2D area connection and you have a weir coefficient associated with that, and you have fairly small cells that are bounding on both sides of that SA2D area connection. If you ever have a situation where you have a lot of water moving over that SA2D area connection, the depth of water moving over that weir causes the computations across that SA2D area connection to compute a flow that's very significant. And thus, if your bounding cells are pretty small, what can happen is those cells will basically empty with volume at a certain time step because it's basically drawing all the volume out of those cells, and then that can lead to sometimes some instabilities on one side of that SA2D area connection. Is that a similar, I guess, thing to note is when you are connecting pump stations to individual 2D cells to make sure that the cell you're connecting it to is not too small in regard to perhaps the peak volume that is going to be withdrawn from that cell?
Yes, you need to think about that, and that can happen, and there's ways around it though. However, it's not going to be near as bad as with the SA2D structure and the Weir equation. Other problem with the Weir equation is not only the volume in the cells, and it's not that it can't handle the small cells, it can. You just have to use a really small time step.
Sure.
Right?
Yeah. Fair enough. Yeah.
But the other problem is that when you have water going over an embankment and you're using a Weir equation, if the water on both sides is almost the same elevation, well, in RAS, it has to use this curve to account for submergence. And the curve at high submergence is rapid bouncing of water and big changes in flow. It's large changes in flow for small changes in water surface. And that causes then the bouncing because you get big fluctuations in flow for very small water surfaces. And that's really the problem. It's the Weir equation and how we handle submergence on a Weir equation. Okay. Whereas if you were using SA2D structure and you said, well, forget the Weir equation, just compute it with 2D equations, you could still get some, water surface kind of going up and down, but it probably wouldn't go unstable because it wouldn't be nearly as bad. Okay, with just solving it with the 2D equations. And that's going to be more like this. This pump, basically the way it works is at a cell, there's basically a source sink term for every cell. And so a source term means you're going to add flow in, a sink means you're going to pull flow out. And so here where the water is being drawn, it's a sink term. It says for a given time step, I want this much flow, and that much flow over the time is a volume. Give me that volume of water, okay? And then it's going to give that volume of water over to the other end over the time step. Now, if that volume of water is much bigger than the volume of water in a cell, yeah, it's going to drop the water surface of the cell. But remember, there's still water coming into the cell over that time also. So depending upon how efficient it is at pulling water in, it may not completely go dry.
Sure.
Okay. But it might bounce too much. And then what you're going to see then is you either need to drop the time step, okay, if you want to keep the cells the same size, or you need to make the cells larger so you can keep the larger time step.
Yeah, even just that one cell where the pump is drawn out of, right? Because then you have more storage, and so it's less likely to draw out.
Absolutely.
So it could be a situation where maybe you just go through and manually remove some of the vertices or the points around that 2D area to make that cell itself a little bit larger.
Yeah, or you could put in a refinement region.
Sure.
And then just use a larger cell size inside the refinement region.
Yeah, which is not something not something I'm used to doing. It's usually the other way around. So that's a good point.
A lot of people don't realize that, but the refinement region can be used in both ways. It can be used for coarsening as well as refining, making it smaller. So, and I use it a lot for coarsening in overbank areas. Yeah.
Okay.
So that's pumps.
Awesome.
That's
cool.
Exciting. Chris and I finished a project within the last year where we had multiple pumps connected. It was for a drainage district down in Texas, and so we had multiple pumps that were draining out a pretty large area. And the whole thing was a 2D model, but we had to connect the pumps to storage areas, which we connected to the 2D areas, and so there was a lot of connections, a lot of things going on there. It worked, but
it actually worked really well. It's just more complex, a lot more pieces to it, and not as elegant as
not as
it
pretty
is with this way.
Yeah, I've made many a model where I had those dummy storage areas just so I could hook a pump to it myself. So. Yeah, so this was definitely another one of those things that was really needed for 2D modeling, and now we have it. So there it is.
Cool.
Yeah.
Awesome.
I did want to talk about computational speed because whether you realize it or not, computational speed always becomes a thing whenever you talk about 2D modeling. Okay. Yeah. And it's unfortunate, I think, that people compare 2D models based on computational speed, because I really don't think that's that important. Yes, it's important. Of course, you want models to run faster. But quite frankly, if you really sit down and thought about it, what's more important is how accurately can the model depict what's really happening and how easy is it to use? Those are, to me, much more important than computational speed. Now, if the model just took forever to compute, yeah, that's a problem, but that's not what we're talking about. There's lots of 2D models out there, and they're all pretty efficient. Yes, computers are getting faster and they're getting better, and of course, we want to make RAS as fast as possible, as efficient as possible. And so we're constantly thinking on how can we improve this, how can we improve that. So one of the things we worked on since 5.04 actually was computational speed. And one of the things we did early on is we had a matrix solver that was allowed the cells to be non-symmetric, meaning that from the center of a cell to the next center of a cell, the face didn't have to be perpendicular to the line that connected those. Okay, but the reality of it is the way the RAS makes the mesh, it enforces that anyway, and so it enforces the mesh to be symmetric in that sense. And so because our mesh forces that, we switched to this other matrix format called a symmetrics matrix format, and symmetric positive definite solver is what it's the official term. And that simplifies the math from the solver, and if the math gets simplified, meaning there's less math, it's going to run faster. Okay, and so just that switch where now we enforce every cell, the face has to be perpendicular between the line that connects the two centers of the cell, and it's assumed to be the case, has allowed us to switch this definite solver. That increased the speed a lot. But another thing we did, go ahead, Chris.
Yeah, sorry to interrupt you there, Gary, but it dawned on me that there may be a lot of users out there that don't know what we're talking about when we say the matrix. Do you have like a quick explanation of what you're talking about when you say the matrix?
Well, the matrix is you take the nonlinear equations and you put them into a matrix solution format, and then there's all kinds of matrix solvers that can solve nonlinear equations, right? And from very simplistic to very complex. And it's a long, deep discussion, so I'm not going to go into it too much. But there's all kinds of stuff you can find on how to do basic matrix solutions for mathematics of nonlinear equations on the internet. And so I would just look up some of that stuff.
Yeah, so you essentially have an equation built to solve full momentum over a face, right?
Yep.
In a 2D area, and you can have thousands, tens of thousands, 100,000, millions of faces. Each one of them gets an equation, right?
Right.
Or actually two equations, because you're also doing conservation of mass.
Right. And then you're doing it in 2 dimensions.
And in 2 dimensions, right. And so you have potentially thousands, tens of thousands, maybe millions of equations all solving simultaneously in this one big matrix. And there are solvers out there that will solve that mathematically. And I don't know how those work, but it's a good thing that you guys do, Gary, because I don't know how else you would do it.
Yeah, well, a lot of these solvers come with the compilers that we have. So we didn't develop the actual, like RAS uses what's called a Paradiso solver, and that came with the Intel Fortran compiler. So we didn't develop it. We're just the benefactor of using it and understanding how to use it. Okay. Yeah. So I don't want to take credit for that because I didn't do that. In fact, nobody in the RAS team did. That came from Intel.
And, do you have to buy that?
Well, it
Did you
came
have
with
to
the
buy it? Or?
no, it comes with the Fortran solver. It's there.
Oh,
It's
okay.
it's part of the math package that comes with it. So,
Oh, very cool.
so that's there. The other thing we did is we further parallelized the code. There was a lot of stuff that goes into setting up the matrix. In other words, computing coefficients, okay, computing, friction terms, etc. That wasn't parallelized in the previous version. We parallelized all that. So that also dramatically speeded up the code. So these two things are what we did to speed up the code to this version. And the benefit of that is here in this table, I've got several data sets. How many cells are in those data sets, from a very small data set up to one that has 2 million cells. And this shows I was running FEQ, means finite full equations, okay? And diffusion wave is DIF. Here's the computational time running that data set in 507, changing nothing but running it in 6.0. Here's the computational time. And then the speed factor is just the 6.0 time, the 507 time divided by the 6.0 time in seconds.
Mm-hmm.
So you can see that most of these data sets are 50% faster, 80% faster, some are 30, 40. But if you average all of them, about 50% faster for all these data sets.
Wow, that's great.
Is there anything in particular, and this might be kind of too high level, but anything in particular about these individual data sets that, for instance, the ones that were 1.8 times faster had this component to them as opposed to the ones that were 1.2 times faster had this?
There's more speed factor for the full equation than there is diffusion wave, which you can see from this.
Sure.
And that's because there's more terms to pre-compute to set up the matrix each iteration of each time step. And since we parallelized that, there's more benefit. In other words, there was more computation time required for the full equations, and parallelizing it got more benefit out of that. Whereas the diffusion wave has less terms, so there was less benefit to what we did for there, and that's why. So full equations, which is great because it takes longer to compute anyway, is going to get more benefit. Mm-hmm. But it's not, there's a lot of factors though. There's still going to be, well, how much the model iterates first, if the model's iterating a lot, like this one, this test number 7 has a lot of iterations, and so there was not as big a benefit because iterating was causing the control of the time anyway.
Interesting.
Okay.
Yeah, that makes sense. Okay.
So models that run really well to begin with and are very computationally stable are going to see more benefit also.
Okay. Yeah, that's great. That's that kind of exactly what I was getting at. So that makes sense.
I've been hearing a lot, Gary, or seeing a lot on social media, people commenting on the nice speed improvements in 6.0 already.
Yeah, there was one guy that
notice. Yeah.
There was one guy that I saw post on the Facebook RAS page that his model ran literally 3 times faster, and he had a large model that was taking almost a day to run, and now it's down running in a like 4 or 5 hours. Wow. So he got a tremendous speed up. So there is a lot of model dependencies with this. This is just the average kind of thing you'll see for most data sets. But that's not all. There's more. Well, we added some additional solvers. So right now, out of the box in 507 and in 6.0, RAS uses a Paradiso direct solver. Okay. What's really great about the Paradiso solver, it's a very stable solver for nonlinear equations, and as far as conserving volume, but it can be slower. There's another type of solver called iterative solvers, okay, that instead of directly solving the equations, they solve them and then they solve them again iteratively. However, on the surface that might sound slower, but in the reality is it actually, for some data sets, it's potentially much faster with these iterative solvers, okay? And so we're getting into the intricacies of solving the matrix versus solving the equations, which is a whole nother iteration scheme, okay, outside of this, solving the matrix. So I'm just talking about the part of solving the matrix, okay, with a direct solver versus an iterative solver. So these iterative solvers, each iteration is much faster than direct solver, but if it takes a lot of iterations, then it might end up being slower, okay? But if it can do it in 1 or 2 iterations, then it's going to be faster. So these iterative solvers have the potential to be faster. However, they require kind of some user-controlled solution tolerances, which we have defaults for in RAS. And they also, in some cases, might be potentially less stable. They might produce a model that's less stable. So what I've found, if you have a model that's on the verge of instability and it runs, if you switch to one of these iterative solvers, it's probably going to go unstable. But if you have a model that runs stably you switch to one of these iterative solvers, it's probably going to run faster and still remain stable.
Ah, great.
So here's
Okay,
those.
very cool.
So here's some experiments. Now this is just solving the matrix. So if we have, in this case, 7 solvers. Now we didn't put all 7 of these into RAS. We ended up with, I think, 3 additional ones. But if you say the Paradiso solver is the standard, and you say that's a unit factor of 1, in just solving the matrix, some of these iterative solvers for this data set were down to 10% of the time.
Wow.
Okay, this one was about 25% of the time. This one was 0.05% of the time to solve the matrix.
20 times faster.
20 times
basically,
faster.
is what you're looking at there.
Yeah.
Wow.
Now in this data set, Paradiso here, and these 2 solvers, 20% of the time and 10% of the time. Now, this is just solving the matrix. Remember, before you solve the matrix, you have to compute all these coefficients that go into the matrix. That isn't changing this. And in between iterations, you have to recompute all hydraulics. Okay, like if you have a connection between across a weir or an SA2D structure. So it's not improving that. It's only improving solving the matrix speed. So you're not going to see 20 times faster models running. It's just the matrix part of it is 20 times faster or 10 times faster or 5 times faster. So I took those same data sets, and here were the times for 507, and here's the 60 using the default solver, which is Paradiso and RAS. And then I ran and I played around with the solvers, and I grabbed the best iterative solver. And so now these times are comparing from RAS 507 to RAS 60 with the iterative solver. Now you're, for some of these data sets, you're seeing 3 times faster, 4.7 times faster. However, there's 3 data sets that were slower. Okay. So the ones
Cary,
in red were actually slower with the iterative solvers.
You pointed out that the EU test number 7 had a lot of iteration to it.
Right.
But that one actually saw an increase in speed. Why would that be?
Right. Well, it wasn't enough iteration to make it go unstable or cause the iterative solver to dramatically have to iterate more. It may have ended up iterating more, but even though it iterated more, because each iteration was faster, the net effect was it still was overall faster.
Interesting. Okay.
Yeah. Now, Truckee River is a combined 1D, 2D model. Okay, and it's 2D diffusion wave in the overbanks. And so the iterative solvers, it just didn't work out. Okay, because there was a lot of stability due to the combined 1D, 2D type stuff. And then this 2 million cell one is a watershed level model that was running diffusion wave. And it seems to be more benefit to some of this with the full equations than there is with diffusion wave. But this is a case that because it was a whole watershed, there was a lot of steep terrain. There's a lot of cells with shallow flow that were iterating a lot during the shallow flow. And when you went to the iterative solvers, it iterated even more. And given that the iterative solver was faster, but it had to iterate more, the net benefit was less benefit.
So if you have a larger model, and maybe a model that you're going to have to run for a number of different scenarios, multiple times, maybe it's a dam breach model where you're running a bunch of different dam breach analysis, it's probably worthwhile once you have the model stabilized and kind of where you want it from a stability standpoint to test it with these 2 different solutions and see which one's faster, so then moving forward which one to use, because that's a significant difference.
Right. So as always, the default in RAS is the thing that's more stable. The Paradiso one is a more stable solver, but it might not be the fastest one. So absolutely what you said, Ben, is what you want to do. You want to get it up and running with a default Paradiso solver, get a stable model as best you can, and then try these iterative solvers. If you're still working on instabilities in areas, don't even bother trying the iterative solvers yet, because you might be wasting your time. Get the model up and running and get it stable, and then try the iterative solvers, and you might see some of these dramatic speed improvements. So like, look at this model. Took 1 hour and 10 minutes with 507, now down to 15 minutes in 6.0 with the iterative solver. Almost 5 times faster.
It's crazy.
Yeah.
Wow. Did you get an opportunity to test out the results and see how they change between these different solvers?
The results are basically the same.
Okay.
If it solves it and it doesn't go unstable or it doesn't cause more instability, then the results are going to be the same. Now, if it causes more instability, in the area of those instabilities, there are going to be some different results, yes.
Okay.
But if it's not causing more instability, then you're basically going to have maybe not exactly the same answers, but very similar answers. So these models pretty much all ended up with virtually similar answers, not exactly the same, but extremely similar answers. You know, we're talking hundredths of a foot differences in the water surface, not tenths.
Right.
So, yeah.
Huh,
Okay.
That's cool.
Yeah.
Yeah, I mean, it makes sense. You're still solving the same equations. It's just you're solving them differently, or you're
Right.
inverting the matrix differently, I guess is a better way of putting it.
It's a different approach to solving equations, yeah, in
Yeah.
in matrix solutions. I'm not a iterative solver expert, so I'm not going to spout off on all the intricacies of it because I'm not up on it. But we have a guy on the RAS team, Alex Sanchez, who is up on it, and he's the one that coded all these iterative solvers. So all the benefit goes and accolades go to Alex Sanchez for that work. He did all that.
Nice.
Yeah. The 3D viewer was something I've wanted to add to RAS forever. And a couple of years ago, we got a new computer science guy on the RAS team. His name is Anton Roder-Siren. And I thought, well, what the heck? Anton is just fresh out of school, right? He's super cheap. He's, you know, no offense, Anton, if you're listening, but when you start out, you don't cost much, right? You're the lowest guy on the totem pole, and your salary is low, okay, compared to the rest of us. And so it's like we can put him on a lot of hours on this for a very little money. So I just kind of took a little bit of money off to the side, begged, borrowed, and stole from a couple of accounts, and said, "Hey, Anton, let's just see what we can do." And he just literally took off with it. I was really amazed at what Anton was able to do in short order for not a lot of money. And so what we have is a 3D viewer, which you can see the terrain and the water surface, and you can show the water surface as depth, water surface, velocity. You can do the velocity tracers. You can fly up and down through the thing. You can create a flight path in RAS Mapper and then have it automatically follow that flight path. There's a bunch of things you can do, and all of this was programmed by Anton. So I got to give Anton all the credit. He really has come a long ways on programming for three-dimensional viewing, and he's learned a lot, obviously. But he really got after this and really took off with it, and he deserves all the credit for this. This is just kind of something I wanted, and he made it really happen.
Well,
Chris,
Anton gets to stick around for another year or so, huh?
He gets to stay much longer than me. They're gonna ship me off way before him.
Nice job, Anton. Yeah, well, you know, this Anton will be happy to hear this if he doesn't already know it, and I'm sure you will too, Gary. But when beta was released, within a day, I was seeing people posting their 3D visualization on Facebook, on LinkedIn, and I mean that was the very first thing that people were talking about. So.
I
If they
do
didn't
need to
know
also
about it
give
ahead of time, they know about it now. Yeah.
right. I do need to also give credit to Alex Kennedy, because Alex Kennedy has been on the RAS team now. I'm going to say this wrong, probably 8 years now. And he was our first true programmer. Everyone else on the RAS team is an engineer that programs. And Alex Kennedy, we brought on about 8 years ago, and Alex has been the spearhead of a lot of the new things you see in RAS Mapper were programmed by Alex Kennedy. And he worked with Anton at the beginning of this to formulate how we were going to approach this 3D tool. So I got to give Alex Kennedy some credit on this too. Anton did, by and large, the lion's share of the work, but he got some help from Alex Kennedy early on developing the 3D viewer. So,
well, shouts to Anton. Shouts to Alex.
Yeah. Wasn't Alex Kennedy, wasn't he the developer of the particle tracing?
Yeah, a lot of things in RAS Mapper are ideas that he and Mark and Cam had and myself, but then Alex kind of said, okay, well, here's how we can do this from a computer science perspective. Okay, so yeah, Alex and Anton are the two true computer scientists on the RAS team, and we are really happy to have them because over the last 8 years, thanks to Alex and now Anton, we've been able to dramatically go faster in what we can do and develop as far as tools and what we were doing as engineers that program.
Yeah, I remember when I was there, Gary, we were just a bunch of hydraulic engineers trying to figure out how to program.
Right. I mean, Mark is the closest thing you have to a true computer scientist, because Mark is, I say, half engineer, half computer scientist.
Yeah.
So,
yeah, that's true. He was, well advanced by the time I got there in computer science, but still his background was hydraulic engineering.
Yeah, absolutely.
And, so we all had we all started there and learned how to program versus now you've got dedicated computer science programmers on board who are learning a little bit about hydraulics.
Absolutely. In fact, they have to.
Yeah.
In other words, to be effective, to program something, you have to know something about how it works.
That's right.
And it's amazing from when they start on the RAS team to now how the different language they speak. They speak hydraulics now.
Cool.
Which is really cool.
Well, Chris, I hate to say it, but as cool as the hydraulic design button is, I think Anton's legacy of the 3D visualization tool is going to trump that.
Oh yeah, that's without a doubt, without a doubt, and that's perfectly fine with me.
Okay, so I'm not going to go into this in detail because I know you're going to bring Cam on, and maybe you can bring Anton on too. As a team, and you're going to do RAS Mapper and you can do the 3D viewer, but I couldn't help but show it. But this is just an animation from it's our friend Bald Eagle Creek and there's Sayers Dam, and we're looking at it in 3 dimensions, and I'm filling it up, and it's going to go over the emergency spillway on the right. And I'm plotting water surface and velocity, so the colors are velocity based. And this is a complete 2D model. So you can animate it, and you can also drive it, you can fly through it. Now you can fly through it with your keyboard and your mouse, but you can also hook up a game controller. So Anton programmed it so you can use your keyboard and mouse, or you can use a game controller. And so if you're a gamer, you're going to hook up your game controller to your computer, and you're going to run this thing with a game controller because that's the easiest way to do it. It's much easier to fly with the game controllers than it is to use your keyboard and your mouse. But here I'm turning on the velocity tracers. You can do that. Anton has a kind of a one mode where it actually looks like the water surface, and it does complete lighting and shading, so it looks like the surface of the water surface and the sun shining on the water surface. There's an option for that. So it's really cool. I'm not going to go into all the details because you can get that in a later podcast. But I couldn't help
Ben,
show it for this.
we gotta put in an order for some game controllers now. Our procurement's going to say, "What the heck are you doing? This isn't playtime."
I was going to say, parents around the country, instead of giving their kids game consoles next year, they can download HEC-RAS on their computers, and they can just goof off and learn skills like this. So
yeah, I can maybe see where this is going though, Gary, and we'll get into this with Cam and Anton, but maybe a little virtual reality kind of worked into this.
Oh yeah, so we went this far on basically a shoestring budget.
Yeah.
Thanks to Anton. Okay, and a lot of help from Alex, and then a lot of ideas that I kind of forced on them what I wanted, but they really made it happen. But the next phase of this is to be able to drape over aerial photography. So instead of seeing the terrain, and then the next phase after that is to have building models that you put in that are vector-based graphics of buildings.
Yeah.
Okay. And then from there, actual virtual reality, putting on the 3D goggles.
Well, the other thing that naturally comes out of this too would be, maybe for a dam breach analysis, actually having the terrain breach itself.
Yeah, right now when the breach occurs, it doesn't modify the terrain in the 3D viewer.
Yeah.
But that could be a future thing also. And then having hydraulic structures that you add in RAS, like let's say you add a bridge, then plotting the bridge in 3D in the terrain. It doesn't do that right now either, but that's a future thing also.
Well, Gary, we touched on it just a little bit just now, I guess, but I do want to ask, and I hate being this person because, the release of 6.0 it's a monumental achievement. It's really, really cool. We really appreciate you coming on and talking with us about it. But I guess I do want to be the one to ask, what's next? I know that HEC is always kind of looking forward. You guys, it seems like you guys never sleep. You're always working towards something else. So I'm sure there's some cool things on the horizon that, after folks have the chance to digest all this new information or new features and work with them, they can start looking forward to next. So if you just want to tease out maybe some ideas that you guys have for
the
future version.
The reality of it is whenever we make a release, there's always a bunch of stuff that we're working on that didn't get released because not everything makes it to the release. So, okay. Some of the big things we're working on, huge things, is there's going to be some intermediate releases of RAS 6, like 6.01 bug fix versions. There's probably going to be a 6.1 or 6.2 with some intermediate capabilities. And those intermediate capabilities are going to be things like we're working on actual true pressurized pipe systems. That's going to have where you just lay out a pipe instead of cross sections, and you lay out junction boxes and drop inlets and pipe changes and bends. And you'll be able to connect the pipe system to the 2D surface. So you'll have a 2D on the surface and a pipe system on the bottom. So we're working on that. And we've been working on that for over a year. And I got a shout out to Chicago District of the Core. They're paying for that.
Wow.
Straight out of their
cool.
budget, because they have obviously a Chicago tunnel system is a big application of that, and so they're paying for that. So that's being worked on. Another thing we're working on that you'll see some internet releases is stuff we're doing for FEMA. My whole career I've been trying to work with FEMA, and 2 previous times I came really close to working with FEMA and getting funding from them to do stuff for them, and it just didn't work out. And so I've been working 35 years, and this is my first time actually being contracted by FEMA to do work.
Nice.
So it's hard to believe, but it is. But it's really cool. They're funding us to do quite a few things. They're funding us, first of all, for some additional speed capabilities that's going to come out in short order. They're funding us to do 2D floodways, which will come out probably in a couple years. Okay. And another really cool thing they're funding us for is to do a GPU solver. So a solver that runs on the graphics card. So we're just getting started on that. So a future version of RAV, there's going to be a GPU solution solver for 2D that hopefully will run 10 to 100 times faster because you can run it on a graphics card and make use of, 1,000 processors instead of 24 or whatever.
All right, let's order some new computers now too, Ben, to go with our new game controllers. We can do GPU when that comes out. When is it? Next year, right?
No. That's going to be a couple of years. We're just getting started on that right now. So, and then the last thing I'll tease out is we've been working for a couple of years now on a completely new user interface, completely redone from scratch, throw out everything and redesign. So we redesigned the user interface. We've got a complete design. We actually started programming it. We got a skeleton interface already going. And the basic premise is it combines the RAS main window, the RAS geometry editor, and RAS mapper into one screen. So you always have a map that's like RAS mapper. You always have buttons for the editors right there, like the geometry editor. You always have the file menu system like the main RAS window. And you have ability to get graphics output and input editors and the RAS mapper kind of spatial layout for bringing in spatial data and doing the maps all in one interface. But there'll still be buttons you press, like the bridge editor is still going to pop up and look like the bridge editor, a separate window, and so forth. Yeah.
Are you going to keep my HD button?
We are. We're going to keep the HD button.
Oh, wow. That's an upset right there.
Yeah. All right. It lives on.
Yeah. Now, when that comes out, that's going to be called RAS 7.0. So, but that's going to be a while before that comes out. So, but that is something we've been working on actually for a couple of years now.
Well, that's
awesome. And very far along on it. So
that's what people love about HEC-RAS. It's obviously it's a great program. It's free. Which is obviously a huge draw for a lot of folks, but HEC is always pushing things forward, and we really appreciate that, Gary. I know everybody in the hydraulic modeling community really appreciates all the work that you guys have done on this software release in particular, but also understanding all the stuff you guys are working on moving forward. So that's really, really neat. Cool. Well, Chris, let me just quickly read out our sponsor thanks for this episode, and then I'm going to share some details on our class, and then I'll kind of let you close us out.
Sure.
So for those of you guys who are watching the previous episode as well as this episode, both were sponsored by our firm, Kleinschmidt Associates. We're very thankful for them for allowing us to do this. Kleinschmidt Associates is known throughout the industry as a firm that provides practical solutions to complex problems affecting energy, water, and the environment. You can learn more about Kleinschmidt at kleinschmidtgroup.com. Speaking of Kleinschmidt, we also, along with this podcast, Chris and I have the opportunity to teach online at this point because of COVID, 1D, 2D HEC-RAS class. Are you guys able to see this ad right now?
Yeah, I see it.
Very cool. Yep. So just wanted to pub this out for folks who are listening to this podcast. Chris and I will be teaching our third online 1D, 2D modeling class. This one will be done in the new 6.0 version. For those of you guys who are not familiar, the class format it's over 6 weeks, once a week, and it's a 4-hour session in the morning from 8 to noon Pacific time. We're going to start that class on February 17th, and it's going to go for 6 weeks. So if you're interested, please either email us at HEC-RAS@kleinschmidtgroup.com, or check either Chris, or Kleinschmidt's LinkedIn page. There'll be a lot of information on there. We're going to obviously learn how to build and run troubleshoot 1D, 2D HEC-RAS models. And then we're also going to cover some new topics, including some of what we talked about today with Gary. And you'll have the opportunity to actually practice modeling a 2D bridge in one of the 1D, 2D workshops that we go through, which is going to be a really
I'm making that workshop right now. In fact, I'm in the middle of it, and so it'll be ready for the class.
Very cool. So yeah, we're really excited for folks to be able to join us for that. We do anticipate that this is going to fill up very, very fast. So if you're interested, please reach out to us right away when the registration link goes out. Sign up right away, because we will probably have to cap this class, and we don't know exactly when we're going to be able to do the next one. So sign up as quick as you can. All right. Well, that's all we have for today. Let me just say thanks, Gary, so much for joining us. I know I really appreciate it. Obviously, I understand, part of the reason that we're fortunate to have you is Chris and your relationship, but it means a lot to me and to Kleinschmidt that you'd be willing to join us. So thank you. And Chris, I'll let you close this out.
Yeah. Thanks, Gary. Means a lot to me too. It was great having you on and sharing all this cool new stuff you guys have been working on. So really appreciate that. People are super excited about it. I'm excited about it. I can't wait to talk about it in the class coming up. I might just run this vodcast and then I can leave the room and just let them watch that. But no, just kidding. But yeah, thanks, Gary. Hey, one thing I want to say too to everybody out there, because there are a lot of people who do HEC-RAS modeling, and inevitably questions come up. You run into trouble, you run into problems. Number one step should be to read the manuals. Okay, these manuals are so well written. I mean, if you've ever read a manual from some other engineering software, you'll know what I'm talking about. The HEC-RAS manuals are easy to read, they're informative, they're very detailed, everything's in there. So make sure you read those manuals, and they'll help you get through it. And also practice with the practice data sets that come with the software. So if you're not aware of that, when you download the software, you can download practice data sets and all this stuff that Gary showed you. I think most of it, if not everything we talked about, Gary, you have in some of these data sets, right?
Everything we showed except for the Hurricane Laura stuff is not in the data sets.
Okay.
Yeah, but everything else.
You can see an example rainfall. You can see example bridges. So yeah, give those a try. And Gary, you got any parting words or anything else you want to shout out to HEC-RAS Nation?
I just want to say, hey, thank you for having me. This is actually a lot of fun for me, and I really like what you guys are doing with the vodcast. Like I said, I've actually watched every single one of them.
Yeah, all right.
Awesome, I think it's cool, and it's nice to see people outside of HEC doing things like what you guys do with both the vodcasts and the RAS Solution channel and the LinkedIn page and so forth. And it's really helping a lot of people. So you guys should be proud of yourself for what you're doing too, because you are both helping a lot of people, and we really appreciate that. So thank you.
Awesome. That's good to hear.
Yeah.
Thanks, Gary. Well, I can't wait till COVID's over and Ben and I can come down and we can hang out at University of Beers or something over there in Davis. And
and you owe me a few beers, and you know what kind you owe me, right?
Man, I owe Gary more Yingling beers than I think minutes in this vodcast. So
that's awesome.
But I'm slowly paying that debt off. But
there you go.
Anyway. And we'll be able to get Yingling here pretty soon too, in person on the West Coast. So that's awesome.
Yep. Yeah.
But anyway, yeah. So again, thanks, Gary. Appreciate it. And Ben, I'll turn it back to you to close us out.
Yeah, and Gary, obviously it goes without saying, but anytime you want to jump on the podcast with us and talk about something with the new version, or if you want to just talk about something you think is interesting in the world of hydraulic engineering, we're always game to have you on. So thank you again. For those of you guys who maybe stumbled upon this video, we do have a video, the previous episode, which was the first part of this. So I would encourage everyone to go back and watch that if you haven't. A lot of good information on that first part of this video series here with Gary Brunner. And with that, this has been Full Momentum and HEC-RAS Vodcast.